Okay, so I'm going to derive the heat equation for a rod. We're going to assume constant thermal properties, no sources or no sinks within the rod, but we are going to assume something that we didn't assume in class, or we're not going to assume something that we did assume in class. We're going to have a constant or a variable cross-sectional area. So I'm going to draw the rod like this. Okay, and I want you to derive the heat equation, and this part about by considering the total thermal energy between A and B. I don't want you to do the thing where you say, okay, for a small slice, we're going to approximate that the energy in that rod is equal to something, and then go from there. What I want you to do is say, okay, if this is A and this is B, I want you to compute the total energy within that piece using an integral. Use a conservation law to relate that to other variables, and basically sort of do it in a more rigorous way, I guess. Okay, so this is just going to be a representative segment. We know that the total thermal energy in this is going to be equal to the integral from x equals a to b, okay, times what? Well, remember, E of xt is the thermal energy density per unit volume. Okay, and again, we're also assuming, I didn't say this, but we're assuming that the rod is insulated laterally so that heat isn't flowing up or down. So thermal conduct or thermal content, heat energy content in the face of the rod is going to be constant. Okay, so this is going to be A of x times the energy concentration E of xt dx. This is the total thermal energy in that part right there. Again, E of xt is a total thermal energy per unit area. So on the face, the total thermal energy, so at a point x, the total thermal energy on the face, you can think about it as being that right there. And then we integrate over all of the faces to get the total thermal energy in this segment, the one that I've sort of shaded in here. Okay, by the conservation of energy, we know that the only way that energy changes in that segment is by energy flowing in or energy flowing out. And remember, phi of xt equals energy flowing to the right per unit area, per surface area, per time. Okay, it is the energy flowing to the right per unit surface area, per unit time. So what this means is that the change of energy in that segment is going to be rate in minus rate out. The rate in is going to be phi of AT times the area at A. So phi of AT, that gives the total energy flowing per second across that face. Okay, because it's phi is flowing to the right per surface area, so we have to multiply it by the size of the surface area. And then flowing out is going to be on the right-hand side. And again, it's rate in minus rate out, and it's phi at A minus phi at B because phi is the energy flowing to the right. Like this. Okay, so what this tells us then is that the derivative with respect to t of the energy integral is going to be equal to phi of AT times A of A minus phi of BT A of B. Okay, so what can we do with that? Well, I can put the derivative on the inside. Since it's a t derivative and an x integral, the integral becomes the integral from x equals A to B, A of x, ET, dx. And by the fundamental theorem of calculus, notice this is kind of like a fundamental theorem of calculus looking thing. We've got a function evaluated at one point minus a function evaluated at another point. The only difference between this and how you normally see the fundamental theorem of calculus is that we have the function evaluated at the left endpoint minus the function evaluated at the right endpoint. So by the fundamental theorem of calculus, this is the integral x equals A to B times the partial derivative with respect to x, A of x, phi of x t dx. This is true for every value of A and B. This is true for all A and B. Okay, and so by that theorem that we learned in class, if two functions have the same integral, no matter what the endpoints are, it means those two functions are equal to each other. So this means a of x et is equal to minus the derivative with respect to x of a times phi. Okay, now we also learned in class that E is equal to the specific heat times the linear mass density. So the linear mass density is constant. It's just the cross-sectional surface area that is changing. C times rho times U. And we also saw that phi is equal to minus k naught times ux. So plugging this into the equation, we get C rho A of x ut of xt is equal to the minus sign, and that derivative is going to cancel with the minus sign there. So this is the partial derivative with respect to x, k naught A of x times the derivative of u. Okay, and this is the heat equation. This is the derivation of the heat equation for when we have non-constant surface area.